for having me. My name is Paolo Mangili. I'm a student at the University of Houston. I'm also a research assistant there. My presentation will be about the cislunar Lagrange points as a way to kickstart a cislunar economy for the 21st century. So, a small introduction about myself. I'm a space architecture student, but my projects are far beyond the design of living environments in space. They also encompass economy, sociology, and engineering in the broad sense. And here you can see some of the projects that I've been taking part lately. I'm also a research assistant at the University of Houston. You can see me here in one of the spacesuit mock-ups that I've built during this semester. These are used in conjunction with a virtual reality infrastructure that we're building with a Boeing funded grant. I'm working with another speaker that will be speaking today lately. He's Vittorio Netti, and he'll be talking more about lunar resources, I think. What I want to describe today is a cislunar project which is all about enabling and fostering space exploration industry commercialization at and through Lagrange points for the benefit, of course, of all mankind. The research mission is to provide a solid case for human settlements and space commercialization, to use Lagrange points as a leverage to access the resources that are already in space in order to achieve much more greater degree of sustainability versus what we have today, which is basically and almost entirely a dependent effort on Earth-based resources, which I'll describe in a moment. So I want us to put ourselves in the year 2035. So by that year, we are almost sure that the cislunar space will be very different from what it is today. We will likely see private companies providing more and more services as space agencies look ahead. A new space race has already begun. We will see heavy launchers. I mean, this year, we've seen Starship beginning to fly, even though not entirely successful. Last year, it was the Space Launch System's turn. SpaceX and other space industries, Axiom, Blue Origin, and many studies state that by 2030, we will see lunar bases and ISRU becoming commonplace. Trade studies show that by those years, we will see a clear demand for in-space infrastructures, which means basically that resources management and very large scale production of fuel, for instance. But expansion in cislunar space is limited, first of all, by the orbital mechanics of cislunar space. Fuel prices are very high, payload fractions are very low. If we have to launch a vehicle from Earth, we have to have a launch vehicle which has a payload fraction which is about 1/50th even of the entire mass of the launch vehicle. This is inherently inefficient, and I think we can do much better in cislunar space by exploiting the resources that this region has to offer. So we have to increase efficiency, and we also have to cut off gradually reliance on Earth-based resources in order to achieve a long-term sustainability. This is what it's all about. I mean, the rocket equation developed by Konstantin Tsiolkovsky at the beginning of the 20th century states basically that there is an exponential relationship between the change in velocity that is needed to reach a certain point in space. I mean, if we have to leave the Earth, we have to have a mass ratio in the order of the tens of times. And if we leave the moon, for instance, carrying resources that have been already produced on the moon, we have a much more favorable lunar mass ratio. So we have to build a cislunar strategy, in my view, minimizing reliance on one side, on Earth, and consequent energy expenditure, which is needed to store fuel in space, which is aimed at providing resources from the moon as a replacement for those resources that we have traditionally brought from Earth. So we take for granted the notional lunar bases that will probably be on the moon by the end of this decade or the beginning of the next one. And we want to focus on the next step, so, which is to make those resources which have been obtained by ISRU processes available to the customers. Studies have clearly shown that there is a problem when it comes to this, because the delivery to markets, or the future, the projected markets, which are not existent today, will likely exist in the next few years. The supply chain is not existent today. And so the moon, I'm stating here, I'm quoting from this study, the moon is a virgin territory when it comes to logistics capability. And we have to build that. We have to imagine a management system that will take care of those resources and will make them available to the future customers that will not necessarily need to land on the moon. They will probably have to go to Mars, for instance. But the moon is an important site when it comes to availability of resources, because the moon is full of resources. I'm not talking about only water. So where do we place this ideal accumulation point of resources between the Earth and the moon? Well, there are many candidates, and the largest competitors, I would say, is low lunar orbit versus Lagrange point number 1. Low lunar orbit, it's not ideal when compared to Lagrange point number 1, because there are complex maneuvers involved, strict launch windows, comparatively high velocity changes needed, which enhances in efficiency and therefore exponentially increases the amount of fuel needed. I'm sorry, this is not my phone. I don't know if you can hear it. Anyway. Okay. I'm sorry. Okay. And also, low lunar orbit has creates very unstable orbits, because the moon has a very irregular mass distribution. So orbits in low lunar orbits are not ideal to have accumulation points of resources. So there's a considerable energy needed to be captured and to leave low lunar orbit. Lagrange point number 1, on the opposite side, enables a direct ascent from the moon with no launch windows, comparatively lower velocity changes needed. It is a much more stable location on the long term, and a negligible energy expenditure is needed to be captured by that point. So that's why we've chosen Lagrange point number 1 as the suitable place for the first fuel depot to be built between the Earth and the moon. This is the space station that has been envisioned for 2035. This is the Lagrange Operations and Refueling Terminal, and is comprised of a series of modules that enable a modular expansion over time. So we can also enable economies of scale. Briefly, this philosophy, as I said, enables a scalable infrastructure. And of course, the depot can be expanded as the cislunar space market grows. So we build to foster the tendencies that are coming in space, and we also want to be providing a service and then grow upon that service. We've used many modules and many designs which are basically based on a design analogy with shipping ports, for instance. We have moving elements, space tugs, which are used to move elements in space. We have movable elements like the payload modules, which are used to store fuel and move it from the moon to Lagrange point number 1 and the other Lagrange points as well. And also we have the main modules, which are the fixed elements to be located at Lagrange points, which are used to to create the space station itself and to manage the entire infrastructure. Now, we have to deal with a cislunar delta V budget and payload fractions. As I said, when we have to leave the Earth just to reach low Earth orbit, we have to deal with a payload ratio which is pretty much 1 to 20 or even 50. When we leave the moon to reach Lagrange points, we can achieve a much greater efficiency of 1 to 3. which means 1 kilogram of payload requires 3 kilograms of propellant to be carried from the moon to a Lagrange point. This is comparatively much more efficient than what we have if we would leave the Earth. So that is the idea, to use a small vehicle that is basically a bunch of propellant to bring resources from the moon and make them available into cislunar space. This is the Space Tug, which is a small spacecraft that uses a hybrid propulsion system comprised of liquid oxygen and solid propellant obtained from ISRU lunar mined resources. And the Space Tug is designed to be completely refueled directly on the moon alongside with the payload it carries. And the interesting thing is that it has been designed in such a way that when we leave Lagrange point number 1 and we reach the moon, we refuel everything, we go back to Lagrange point number 1, the Space Tug can make it back to the moon with an empty payload modules, hence creating a continuous cycle that can repeat forever in theory. These are the series of payloads that have been envisioned with the different launch vehicles. We've opted for a reduced number of payloads to achieve maximum efficiency. And also we want to create a symbiotic relationship between the infrastructures that will be already on the moon and what we do to make those resources they will deliver available in cislunar space. The plan for a 5-year assembly timeline for 970 tons spacecraft that will be able to carry that amount of fuel is comprised of about 22 launches at a rate of about 4 flights per year, which is very much in line with what has happened for the International Space Station, which has been assembled over a period of 12 years. But this will be much easier given the fact that on one side, we will have more heavy lifters in a few years, and on the other, this space station, at least in the beginning, is designed to be completely unmanned and remotely controlled. This is a animation that I've put together when we first developed this project. This originally was a group project, but now I decided to carry this all the way for my thesis, which will be presented next year. And the video comprises the first phase of the project, which is basically to create the first fuel depot at the Lagrange point number 1. So the scenario is the 2030s, thriving space industry, lunar infrastructures, and the need for efficient cislunar space logistics that will become evident. So the first flight will be with a space launch system launch vehicle that will carry the first payload A, which is comprised of main module number 1, a Space Tug, a couple of lunar rovers, which I'm going to describe in a moment, and robotic arms for the maintenance of the space station itself. Destination, of course, is Lagrange point number 1, more than 300,000 kilometers from Earth. Solar panels are deployed after arrival at L1. Robotic arms are used to move the lunar rovers away from their storage base, and they will be docked to the Space Tugs. And the entire assembly will eventually be brought to the lunar surface. But this initial phase will be the testing of all the systems. Subsequent payloads will all be carried ideally by the Starship, exploiting its very favorable cost per payload cost, and also their advertised flight rate. This is a big bet, but we hope it will be possible in the next future. So Starship will carry payloads from payload B all the way to payload E, and therefore assist the expansion of the Lagrange point number 1 base. Here we can see the Starship approaching, and this is one of the payload modules. Each one of those modules, which is envisioned to work like a shipping container, can carry about 10 tons of propellant that has been moon mined. The first mission will be, of course, a testing mission with the Space Tug and the payload module leaving Lagrange point number 1. igniting its engines, and getting to the South Pole, where we imagine that lunar infrastructures will already be there. Lunar crews will assist the deployment of the lunar rovers, which will be left on the moon. Those rovers are used to assist the refueling of the space tug itself, because the space tug is designed to have a hybrid propulsion system, which is designed to be refueled already on the lunar surface with a solid component and a liquid oxygen component. This is to achieve a much more favorable mixture ratio of propellants, which does not impinge the quantity of propellant that we want to sell to customers. The beauty of this design is that the payload modules, which will carry the fuel from the moon to Lagrange point number 1, do not have to be unloaded to be refueled because we have pipelines running all the way down the space tug. At the end of the mission, each space tug leaves the lunar surface with its precious cargo and reaches L1, where other modules will be added in the years, adding more and more storage capacity, and therefore creating a very valuable asset for cislunar operators. And now we can see that the space station is increasing its size. The space tug can also become a very important asset because of its flexibility and adaptability. So we will have propellant storages already on site at Lagrange point number 1, and the maintenance capability already there. So in the future, we might see something like this: multiple space tugs carrying tens of tons of propellant that has been moon mined, make it available for customers already in space that do not need, therefore, to reach the moon and therefore expend fuel for just to refuel. I mean, if you have to leave to reach Mars, for instance, you don't need to land on the moon. You need just to refuel and stop by an infrastructure like this that will serve the customer in the future. And again, here we can see the buildup of a very reliable and efficient space tugs fleet. So the resources on the moon are many. Not only water and therefore oxygen and hydrogen, but also regolith, from which we can extract metals, raw alloys, silicon, raw silica, and many other materials, and therefore refined products. I'm speeding up because I'm running out of time. What has emerged from research is that ISRU must operate as a part of a larger infrastructure, which is why we're here. By the 2030s, we can see that the supply chain, we will have Gateway on the orbiting the moon, and we'll have a traditional approach to space. I mean, from the Apollo days during the shuttle program all the way to Gateway, much of all the stuff has been carried from Earth. And Gateway will likely be a small change in that perspective, but we want to do much more than this. So how do we get to the 2050 scenario where we'll have efficient space logistics, space mining, space manufacturing? I mean, those are very bold objectives, but we need a plan, at least a larger plan. We can see that there are differences between national actors and international actors. On the national perspective, we have private companies acting in a much liberal, individualistic, profit withholding way, and space agency acting in a collective, profit reinvestment-oriented approach, benefits share. And on the international side, we have spacefaring nations like the US, Europe, Russia, Japan, acting much like their companies in the international sector, versus non-spacefaring nations who want to redistribute those benefits, which is another interesting tendency. I think, as research has shown at least, that private companies can make things efficient, like access to low Earth orbit, while disruptive innovation can be achieved by public space agencies. And again, the frontier metaphor, which is very, I think, apt to describe our situation. We have a public sector leading the way through dangerous and unproven technical grounds, and a private sector coming in after and making everything efficient over time. Because the public sector is not good to achieve efficiency. NASA faces many costs overruns, while SpaceX speed to market has been much quicker. But SpaceX didn't invent access to low Earth orbit, for instance. It was SpaceX that made it efficient. And so from an space architecture point of view, we have this phased approach, which has a higher project risk, where efficiency is very low at the beginning and efficiency increases, private sector comes in, the innovation level stabilizes, and then another phase can begin, and again, the process reiterates. The big picture, of course, for a space architect then is that one-off efforts, bespoke efforts have to be carried out during the early stages of each CONOP space. A modular design all along has to be enforced, international collaboration to share benefits, and virtuous cycles have to be preferred with modularity. As we said, we want to cut off Earth dependency on Earth-based resources. And one of the ideas is to use moon mine fuel as a leverage to assist the developing market in the space industry and those who want to work in a cislunar environment in the next few decades. First step, of course, is space refueling, because it's the most important asset to move around in space, done with a low number of repeatable modules, which yields a scalable design. And the creation, of course, of supply chains that start directly in space. And using this paradigm, we can expand from Lagrange point number 1 to the other Lagrange points, using the moon as a reserve of resources, which can be efficiently made available into space using the strategy, which will be expanded in the next few decades, ideally. And we can have multiple refueling platforms, not only located at Lagrange point number 1, but also Lagrange point number 2 and Lagrange point 4 and 5. And so we can make logistics, mining, and manufacturing much more achievable. By the 2030s, ideally, we can have those collinear Lagrange points, fuel depots, where refueling basically is the base for all the other activities. And this is another thing I'll gloss over because it's too much stuff. And we can have also manufacturing L1 now that we will have more customers coming in, and therefore the capability to assist them and diversify our business. And so the idea is to make new supply chains, which will start already in space. And new modules to be designed. This is, of course, work that has to be done, but ideally we will expand the activities from just space refueling to space logistics as a whole, space manufacturing, space mining, and other businesses. This is a profit, revenues, and costs equation, which is adapted to our case. Given the fact that we will have a reusable system, an automated system, and we'll have a flow rate of material coming in, we will have some design which can minimize the costs and therefore enhance the revenues and maximize the profits. And these are the key takeaways that have to be taken from this equation, which has been adapted from from a technical economic study. And again, these are the different sectors that have been investigated that can be part of this infrastructure after leveraging the great potential of space refueling. Space manufacturing, for instance, which is not limited to just 3D printing, and many of these options still have to be investigated because not all might adapt to a cislunar environment or a Lagrange point environment, but manufacturing of pharmaceuticals, for instance, because zero gravity can create pure crystals, is a very interesting option. And by the 2040s, we will have expansion to Lagrange point number 4 and 5. And we will have also a flow, ideally, of production, starting from raw materials all the way to semi-finished and advanced products. And we can also have testing areas at Lagrange point number 4, for instance, which is very stable and is the ideal location for example, nuclear propulsion testing. And therefore, as I said before, we will start in the mid-2030s all the way up to the 2050s with supply chains that will start on the moon and in space, because eventually we will involve near-Earth asteroids, and will end in space and even on Earth. Things like precious metals, for instance, can be brought from space. So what is the design destination? I'm nearing the end of my presentation. We want to leverage all these infrastructures to make those scenarios into the realm of possibility and plausibility. So space mining, space manufacturing, efficient space logistics, some of which will be demand-driven, some of which will be supply-driven, but the key cornerstones of this development will be, ideally, in my thesis at least, will be a system of platforms at Lagrange points between the Earth and the Moon. And that's why those scenarios can be made available. There are many obstacles to this. We have idealistic treaties like the Outer Space Treaty. There is no concept of property in space, and those things have to be investigated. I've done some research on this aspect, which is very complicated. There's an underlying conflict between advanced nations and developing nations, the second of which want to redistribute the benefits that will come from space, while the first ones will want to withhold those profits. And I think that something like an international credit system that will allocate portions of the moon or asteroids and even orbits at Lagrange points will be very helpful, because we will have a peer-to-peer basis, a peer-to-peer trade of those credits, which will be much more equal and enable access even to countries which don't have that today don't have access to space, have to rely on spacefaring nations, but also that will enable technology transfer. There are a lot of aspects to this, but I think we'll have to start this discussion quite soon in the future, because this is a very important issue. And again, this is what I've shown earlier, the difference in the national perspective with repeating patterns of behaviors between space agency versus private versus public agencies, and then spacefaring nations versus non-spacefaring nations. Spacefaring nations, which are very idealistic in their talent recruitment, for instance, in their narrative about space, and non-spacefaring nations, which are very pragmatic in their approach. I mean, countries like Colombia, Mexico, Nigeria even, just to say a few of them, they're very specific in their objectives, and they have to justify to their people why they're going into space, why they're spending their limited economic resources into space. And I think we have a lot to learn, in fact, as from this approach. And so this was a very lengthy presentation. I acknowledge that, and had a lot of topics. I hope you enjoyed it, and I'm open to questions now.
Okay, I think then. Okay. Since there is, let me say, Paolo make this very great presentation, visionary in a sense. Thank you very much, Paolo. Since there is now the coffee break, I think that the people in person could directly ask questions to Paolo. The other there on Zoom can write it on the chat, and then we will make them in contact, keep in touch with Paolo for the answer. Thank you very much. We'll be connected again at 11.